Hey, this is Dr. Sweeney. What we're going to be looking at right now is we're going to be looking at some circuits with piecewise continuous EMFs. And so very commonly what will happen is that we'll get a circuit where what we get is a charge or a current that's been put onto the circuit at one set of voltage, one set of amperes for a certain period of time, and then it changes at another point in time, right? Like maybe it's on for a certain period of time and then it turns off after, say, 5 seconds or 10 seconds. And so what we want to be able to do is we want to figure out what is a function for either the current or the charge on that circuit. So let's suppose that we have an RL circuit with a differential equation, and that's given by, and this is pretty standard, this is di dt plus R over Li equal to 1 over L e of t. So this is an RL circuit. That is that it has no capacitance. And we're going to have that R and L are constants, and E of t represents the applied EMF. At t equals 0, we're going to switch the circuit on, and it's closed, and the applied EMF increases linearly from 0 to 7 volts over 10 seconds. The EMF then remains constant, so it remains constant at 7 volts for t greater than or equal to 10. We want to determine the current on the circuit for t greater than or equal to 10. So what we're going to do here, and one of the things that kind of makes something like this a little tricky, is that we've got R over L, and we've got 1 over L, and so we've got a lot of variables in here, but pretty much it's got the same process that we've been using for finding the solutions to differential equations using Laplace transforms using the second shifting theorem. Okay, so what we're going to need to do first is we need to find a function for E of t. And E of t is a piecewise continuous function because they tell us it's closed, it starts out closed, and the applied EMF increases linearly from 0 to 7 volts over 10 seconds. Okay, so we kind of imagine what's happening here, a graph on the function. We've got at time 0 we're at 0, and then at time 10 we're at 7. Okay, so we have this line, this linear line, and that line is represented by 7/10. So it's going to end up being right, because it's y2 minus y1. Okay, so y2 minus y1 over x2 minus x1, and so it's going to end up being 7/10 t, and that's going to be that way from 0 less than or equal to t less than 10. And then it's going to stay at 7 volts for all t greater than or equal to 10. And so that's our piecewise continuous function. You can check that it's piecewise continuous. So now what I want to do is I want to rewrite E of t using the first shifting theorem as a unit step function. So what we see here is first from 0 to 10, so 1 minus u10 of t times 7/10 t. That gives me that first interval, and then plus u10 of t times just 7. Then what I'm going to do is I'm actually going to simplify it. I'm going to end up with 7/10 t minus, and then I'll combine these two, so I'm going to get 7 minus 7/10 t times u10 of t. And that is our piecewise continuous function written as a single function. Now my differential equation is going to be, my dE will end up being I prime plus R over Li equals 1 over L times 7/10 t minus 7 minus 7/10 t u10 of t. And then what we're also told is that y of 0 is going to equal, or y prime of 0 equals 0. The initial current, okay, what we're told is that the switch of the current is closed, and so hence, or the circuit is closed, so consequently there's no current going in there at time 0. Now what I'm going to need to do is I'm going to need to go and find utilize Laplace transforms in order to go in and find the solution to the differential equation. So I'm going to do that, and so I'm going to get L of I prime plus L of R over Li equals L of, and now this is going to be 1 over L times 7/10 t minus, and then we'll have it u10 of t, 7 minus 7/10 t. The left-hand side is going to give us S L of I plus I of 0 plus r over L, big L of I, the Laplace transform of I. So the one L is the inductance, the other L is the Laplace transform. And then this is going to end up equaling, and we can actually separate this out. So we'll do this first part right here. That's going to end up being L times 1 over L. Okay, and so, or excuse me, that's the Laplace transform of 1 over L. So it's going to be 1 over L, and then times 7/10, and then times 1 over s squared, because that's the Laplace transform for t. Then minus, and then what I'm going to do is I'm just going to rewrite this as L of u10 of t, 7 minus 7/10 t, so that we can go over the Laplace transform using the second shifting theorem. What we forgot to do here is we forgot to actually bring in and multiply that by 1 over L. So we're going to do that right there. And so now if I rewrite this and I start using my second shifting theorem, I'm going to get 7 over 10L s squared minus, and then this is going to be 1 over L e to the negative 10s using that first shifting theorem, because this u10 of t becomes e to the negative 10s. And then it'll be the Laplace transform of, and it's going to be 7 minus 7/10, and then this is going to be t plus 10. If we go in and we do a little bit of algebra, basically multiplying 7/10 by t plus 10, what we end up getting is this is equal to now 7 over 10 L s squared minus 1 over L e to the negative 10s. And this whole thing here is just negative 7/10 t. So this will become a plus, and then this will become times 7/10 times 1 over s squared. So if we rewrite this, just kind of cleaning it up a little bit, we're going to get 7 over 10L. And I'll actually take that and multiply 1 over s squared to make things a little simpler. Plus, this will be 7 over 10L e to the negative 10s times 1 over s squared. Now what I've got to do is I've got to actually go in and do a little bit of algebra in order to allow me to go and solve for I, my current. So I'm going to end up on the left-hand side, because I of 0 ends up equaling 0. I'm going to get s L of I plus r over L, L of I. And we're going to just combine those two together. We're going to end up getting s plus r over L, L of I. And then that'll equal this left-hand side right here. Okay? And so I'm going to rewrite that without rewriting that again. And then I'm going to get L of I equals, and this is going to be 7 over 10L. Remember, that's a constant, times 1 over s squared times s plus r over L, plus, again, e to the negative, or 7 over 10L e to the negative 10s times 1 over s squared times s plus r over L. Which is actually kind of what we should expect. We should expect that basically we're going to get something very similar to what's on the inside and the outside, okay? Just separated by this e to the negative 10s, which becomes our unit step function. What I'm going to do now is I'm actually going to figure out what 1 over s squared times s plus r over L is in terms of partial fractions. And so what I'm going to get now is I'm going to get L squared over R squared over XS plus RL, R over L, excuse me, minus L squared over R squared over S plus L over R divided by S squared. So now what I can do is I can rewrite the current L of I is now going to equal 7 over 10L times, and this will be L squared over R squared, S plus R over L, minus L squared over R squared divided by S plus L over R, S squared, plus now 7 over 10L e to the negative 10s times L squared over R squared, S plus R over L, minus L squared over R squared divided by S plus L over R, S squared. And now I have something that I can go in and I can just take the inverse Laplace transform. Remember that L and R are all just constants. So we don't have to really worry too much about this. So what we're going to get is when we take the inverse Laplace transform, we're going to get I of t is going to end up equaling 7 over 10 L. And so let's just pull that all out of there. And then we'll write this as L squared over R squared. And then it's e to the negative R over L t minus, and then this is just going to be the constant L squared over R squared plus L over R. And since it's S squared, it's going to be L over RT. And then plus, we've got 7 over 10L. And now using the first shifting theorem, or the second shifting theorem, excuse me, what we're going to get now is that this is now going to go back to being that unit step function. It's going to be U10 of t. And then we're going to have, this is going to be L squared over R squared, e to the negative R over L, just like we had before, but now we're going to have to do the shift, and the shift is going to tell us it's going to be over to the right 10, so it's t minus 10. We subtract the 10 off, minus L squared over R squared, and there's no t in that one because that's just simply the constant, plus L over R, and then this is going to be t minus 10. Because normally S squared was just going to be 10. Now what we're going to be doing is we're going to be shifting it to the right 10. Yeah, there we go. Okay. So essentially what we're looking at here is we're just looking at in this case, a first order differential equation, a Laplace transform, and using Laplace transforms and a unit step function. So it's that unit step function that kind of makes things a little difficult, and also all of the, the kind of the variables, right? All these L's and R's. But remember, they're just constants. Okay. So if we wanted to go in and we wanted to actually do this with, say, define values for the constants, all we need to do is just plug in those values in the constants into the differential equation, and then construct and then go in and solve the differential equation using the Laplace transforms and that unit step function. So why don't we go and do that in this next example? Let's take a second example, and now this time we're going to put in some values in for, say, for example, our resistance and our capacitance. And it actually simplified things quite a lot because we don't have to put all those L's and those R's in there. But the process is going to be exactly the same. Process is exactly the same, different differential equation, but that's okay. We'll get this. Suppose that we have a capacitor, it's got a resistance of 0.25, and so that gives me that C, our capacitance, is 0.25, or excuse me, our resistance, R, is 0.25, and our capacitance, C, is equal to 0.125. E of t will represent the EMF. For the first 5 seconds, the applied EMF is a constant value of 15 volts. Thereafter, the EMF decays exponentially at a rate of E of t equals 10e to the negative 3 times t minus 5. If the capacitor is initially uncharged and RC is not equal to 1, determine the current in the circuit for t greater than 0. Okay, so what we're looking at here, we've got basically the equation or differential equation for the circuit, Q prime plus 1 over RCQ equals 1 over R E of t. So given that R equals 0.25, C equals 1.125, again, what we're going to have to do is we're going to have to go find E of t. Now, E of t in this case is actually even simpler than the last one. We can see the EMF has an applied value of 15, okay? And that is for the first 5 seconds, so that's t greater than or equal to 0, less than 5. And then at time 5, t greater than or equal to 5, it decays exponentially. We get 10 e to the negative 3 times t minus 5. And actually, to make this continuous, why don't we change this to a 10? Right? It'll start out at 10. And so we'll change this now to 10. Otherwise, it's not piecewise continuous. And so now that's going to be our E of t. So what I need to do now with E of t, I need to rewrite E of t using the unit step function. So we're going to have 1 minus u5 of t times 10. That's for the first set. That's t greater than or equal to 0, less than 5, plus... and then u5 of t times 10e to the negative 3 times t minus 5. Then I'm just going to rewrite this. So this is going to give me 10 minus, or rather, let's do 10 plus u5 of t, and then it'll be 10e to the negative 3 t minus 5 plus, or rather minus 10, pardon me, minus 10. Now when I plug in R and C, what I'm going to end up getting is I'm going to get q prime plus 1 over 0.25 times 0.125. Q equals 1 over 0.25, and then this, 10 plus u5 of t, 10e to the negative 3 times t minus 5 minus 10. And then if I go in and I just rewrite it, I get q prime plus 32q equals 4 times 10 plus 4 u5 of t times 10e to the negative 3 times t minus 5 minus 10. And if we just bring in that 4, we're going to get 40 plus, and then we'll make this 4 u5 of t, 10e to the negative 3 t minus 5 minus 10. So that's my function, or that's my differential equation, utilizing the unit step function. Now what I need to do is I need to go find the Laplace transform. So I got L of q prime plus L of 32q equals L of, and then it'll just be this right-hand side. We'll talk about this. It's going to be 40 plus 4 u5 of t, 10e to the negative 3 t minus 5 minus 10. And so now we get S L of q minus y of 0, or q of 0, excuse me, plus 32 L of q equals, and we got L of 40. I know I wrote it as a 40. It must have just disappeared. L of 40, so that's going to give me 40 over S plus 4L, and this is going to be u5 of t times 10e to the negative 3 t minus 5 minus 10. So this right-hand side, I'm now going to use my second shifting theorem in order to rewrite this Laplace transform right here. I've got 40 over S, and then plus 4. First thing I'm going to do is going to pull out that u5 of t. I'm going to make that e to the negative 5s times the Laplace transform, and now I'm going to need to make a shift. And the shift is going to be, I'm going to add 5 to each one of these arguments. So this t minus 5 is now going to be t minus 5 plus 5, which is just equal to t. And then since 10 has no t's, it just stays 10. So this is going to be the Laplace transform of 10e to the negative 3t minus 10. And so that's going to end up equaling 40 over s plus 4e to the negative 5s. And then the Laplace transform of 10e to the negative 3t is going to be 10 over s plus 3 minus 10 over s. And all of that is now going to equal this left-hand side. Q of 0, we actually get is going to be 0. So this means I'm going to get S plus 32 L of Q when I combine those terms and factor. And so now all I got to do is just divide out that S plus 32 in order to get something that I can then take the inverse Laplace transform of. So I've got L of Q is now going to equal 40 over S times S plus 32 plus 4e to the negative 5s, 10 over s plus 3 times s plus 32 minus 10 over s times s plus 32. Now I'm almost there because I've just got to get these into the form, these into the form, and this into the form in which I can actually take an inverse Laplace transform, something that I know that I can do and I can work with. So I'll start out with this one, the s times s plus 32. And what I get there is I'm going to get L of Q is going to equal, and this will be 40 times, and it'll be 1 over 32 times 1 over s minus 1 over 32 times 1 over s plus 32. Which I suppose we could just take out and make it 40 over 32, or that would be just 5 over 4 times 1 over s minus 1 over s plus 32. Plus, now we got 4e to the negative 5s. we're going to need the partial fractions for s plus 3 times s plus 32. So this is going to be times 10 times, and this will be 1 over 29 times 1 over s plus 3 minus 1 over 29 times 1 over s plus 32. And we'll do some simplification on that one in just a second. And then minus 10, and we already know what this is going to be. This is going to be 10 over, or excuse me, 10 times 1 over 32s, or 1 over 32 times 1 over s, minus 1 over 32 times 1 over s plus 32. And that's 1 over s plus 32. Now I've got, right, 5/4 times 1 over s minus 1 over s plus 32 plus, and then let's pull out these 10s. So we're going to get 40e to the negative 5s times, and this is going to be 1 over 29 times 1 over s plus 3 minus 1 over s plus 32 minus 1 over 32 times 1 over s minus 1 over s plus 32. I suppose we could combine some of these fractions. I'll let you do that on your own. And so now what we get is and now we have something that we can go in and we can find the inverse Laplace transform for. So I'm just going to write take the inverse rather than writing out all of that notation. It's a lot to write L inverse for all of this. Basically, you're going to take L inverse of this side, and we're going to take L inverse of this side. There we go. L inverse of the left-hand side is going to give me Q of t, which is the function I'm looking for. And then that'll be 5/4, and then this is going to be just 5/4, because that's going to be constant, minus 5/4 e to the negative 32t. Plus, and now this is the unit step function, so this is going to be u5 of t. We should say actually 40 times u5 of t. And then times, and what we're going to need to do for each one of these terms, we're going to go and we're going to take the inverse Laplace transform of each one of these terms, but instead of t, we're going to actually have t minus 5. Right? We're going to sub t minus 5 in for each one of them. We're going to shift to the right 5. So u5 of t times, and this will be 1 over 29 times e to the negative 3 times t minus 5. So there's the first part. This would be a 3t, e to the negative 3t, now it becomes t minus 5, minus e to the negative 32 t minus 5, minus 1 over 32, and then this is just going to be constant because it's 1 over s, plus, and this is going to be 1 over 32 e to the negative 32 times t minus 5. And again, you can add 1 over 32 and 1 over 29 to simplify this a little bit further if you'd like to. All right? And that ends up giving us the solution to our differential equation. What you'll notice here, this part right here, that's actually that's your homogeneous part. And then this here, right, the 5/4 e to the negative 32t, that's your homogeneous part, okay? And then this 5/4 and this part right here, they are, in fact, the particular solution that you have to get, okay? And both the 5/4 and the 40u5 of t, they're essentially the part of the differential equation that is the non-homogeneous part, okay? So what did we do? Right? One is we set up the dE, or we set up the piecewise function using the information. Then we set up the dE, and then we solve using Laplace transforms and the second shifting theorem. And that's how you go about doing these particular kinds of circuit problems where you have a piecewise continuous EMF. All right, I hope you got a lot from that. I really enjoyed doing it. This is kind of quick and dirty. We wanted to kind of look at a couple of example problems where we see some of these circuits in action. What you'll notice about this, and any kind of time that you're working with the unit step function or that heaviside function, is essentially we want to set up the piecewise function, then transform it into the unit step function so that we can then take the Laplace transform, do some algebra, and then invert it. If you did enjoy this video, go ahead and press like. If you have any questions or have any comments, please go ahead and put it in the comments. I know there's a lot of calculation in there. If you've got any questions about that, or if you happen to have found a little issue there, please go ahead and let me know. And if you like the work that I'm doing, you want to see more stuff like this, go ahead and subscribe to the channel.